Space is a silent ocean of mysteries we have only begun to explore. Every new telescope and probe sends back data that shatters our old assumptions, revealing a cosmos far stranger and more wonderful than we ever dreamed. In this journey, we will uncover 30 groundbreaking discoveries that have the power to fundamentally rewrite our understanding of the universe and our own place within it. You will see how a gas on our nearest planetary neighbor hints at life, and how ancient galaxies observed by the James Webb Space Telescope seem to defy the laws of physics themselves. These are not just incremental steps, they are potential revolutions. What do you believe is waiting for us in the dark? Our own solar system still holds secrets capable of taking our breath away. The story begins not on a distant exoplanet, but right next door in the swirling, acidic clouds of Venus. For years, we saw Venus as a cautionary tale of a runaway greenhouse effect, a scorched and hellish world where nothing could possibly survive. Then, in 2020, astronomers made an announcement that sent shockwaves through the scientific community. They had detected the spectral signature of phosphine gas high in the Venusian atmosphere. Now, phosphine is a simple molecule, just one atom of phosphorus and 3 of hydrogen, but its discovery here was monumental. On Earth, this gas is only produced in 2 ways, either in industrial laboratories or, crucially, by anaerobic microbes thriving in environments devoid of oxygen, like swamps and the guts of animals. It is a recognized potential biosignature, a molecule that, in significant quantities, often points to biological activity. Finding it in the clouds of Venus was like hearing a faint, familiar whisper in a place everyone assumed was completely silent. The environment there, while still incredibly harsh, is the most Earth-like spot on the planet, with temperatures and pressures that are almost tolerable. This is what makes the discovery so compelling and so fiercely debated. How could this gas exist there? The intense ultraviolet radiation from the sun and the corrosive sulfuric acid in those clouds should destroy phosphine molecules almost instantly. For the gas to be present in the concentrations observed, something must be constantly replenishing it. The most exciting and controversial explanation is that microbial life could be floating high in the Venusian atmosphere, somehow surviving and producing this gas. Of course, scientists have proposed non-biological sources, from unknown volcanic processes to exotic chemical reactions involving sunlight and the planet's surface minerals. Yet, so far, none of these abiotic explanations have perfectly fit the data. The debate rages on, forcing us to reconsider a fundamental question. If life can find a way in the temperate cloud decks of our closest planetary neighbor, a world we once wrote off as utterly dead, then where else could it be hiding? The mystery of life next door was still echoing when the cosmos delivered another enigma, this one from the void between stars. In 2017, a Hawaiian telescope spotted an object hurtling through our solar system. They named it Oumuamua, which means a messenger from the distant past. It was our first confirmed visitor from another star system, and it was unlike anything we had ever seen. The data painted a bizarre picture. It was tumbling through space, and its shape was extreme, a cigar or a pancake hundreds of meters long, but only a fraction of that wide. This was strange enough, but then came the real puzzle, its acceleration. As it sped away from the sun, it did not follow a purely gravitational path. It was accelerating slightly, as if something was giving it an extra push. For a normal comet, this is easily explained by outgassing, the sun's heat vaporizing ice and creating a jet of gas that acts like a tiny engine. Yet Oumuamua showed no visible coma, no tail of gas and dust that all comets produce. It was a dark, silent, and seemingly barren rock, yet it was accelerating anyway. This is where the scientific mystery truly began. The mainstream explanation suggests it could have been a very unusual comet after all, one made of a special type of hydrogen or nitrogen ice that could vaporize without leaving a visible trail. This would explain the push without the telltale cloud, but the lack of definitive proof left the door open for more speculative ideas. Some scientists, like Harvard's Avi Loeb, proposed an even more extraordinary possibility that Oumuamua could have been an artifact of an alien civilization, perhaps a light sail using the pressure of sunlight itself for propulsion. While this is not the scientific consensus, it forces a profound question. If we cannot immediately explain the behavior of our very first interstellar guest, what does that say about the vastness of what we do not yet know? These objects are not rare, they are simply hard to see, and the next one might offer even greater surprises. While we were still puzzling over our interstellar visitor, the universe sent us another kind of signal, one of unimaginable power. These are fast radio bursts, or FRBs. Imagine a flash of radio waves so intense that it releases more energy in a single millisecond than our sun does in 3 entire days. For years, these bursts were complete phantoms. They would appear on our telescopes as spectacular spikes of energy and then vanish without a trace, leaving astronomers with a profound question. What in the cosmos could possibly create such a brief, catastrophic release of power? The first major breakthrough came when we started to catch some of these bursts repeating. Unlike the one-off events, these repeaters gave us a second chance, and a third, and a fourth. This repetition ruled out any source that destroyed itself in the process, like a single, cataclysmic collision. It meant the engine behind these bursts had to be something that could fire again and again. The real game changer, however, was when our most sensitive radio telescope arrays finally managed to do the impossible. They pinpointed the origin of several of these bursts to specific galaxies millions or even billions of light years away. This was a monumental achievement. Think of it like hearing a mysterious, deafening bang in a vast, dark forest. For years, you only heard the sound. But now, you have a precise direction. You know exactly which tree it came from. Locating the host galaxy was the first critical step in solving the mystery. We now knew these titanic explosions were not happening in our own cosmic backyard, but in distant stellar cities, each with its own unique environment. Some bursts were traced back to young, chaotic galaxies furiously forming new stars. Others originated from much quieter, older galaxies. This diversity immediately told us that there might not be just one single cause for FRBs. There could be multiple cosmic culprits, so what are they? The current best suspects are some of the most extreme objects in the universe. A leading candidate is a type of highly magnetized neutron star called a magnetar. These are the collapsed cores of dead stars, so dense that a single teaspoon of their material would weigh billions of tons on Earth. They possess magnetic fields trillions of times stronger than our planet's. A starquake on the surface of a magnetar, a sudden cracking of its crust, could theoretically unleash a blast of energy that fits the profile of a fast radio burst perfectly. Other theories involve collisions between neutron stars or matter falling into a black hole. Yet, the sheer power and bizarre patterns of some bursts have led a few scientists to cautiously float an even more speculative idea. Could some of these signals, especially the highly organized repeating ones, be the result of advanced technology? Perhaps a civilization harnessing the energy of a star to power interstellar beacons or propel massive light sails across the galaxy. While this is the least likely explanation and far from the scientific consensus, it underscores a thrilling truth. By finally tracing these signals to their home, we have not solved the mystery. We have simply begun the real investigation. What we are witnessing could be the death cries of stars, the spin of cosmic magnets, or something else entirely, a signature in the static that we have not yet learned to read. The violent crackle of fast radio bursts from distant galaxies reminds us of the universe's raw power, yet some of the most transformative discoveries are being made much closer to home. For generations, we looked at the moon and saw a barren, airless world, its sun-baked surface relentlessly scorched by solar radiation. Any water, we assumed, could only survive as permanent ice in the deep, cold shadows of polar craters, never seeing the light of day. That fundamental belief was shattered when a remarkable flying observatory, a modified Boeing 747 jet known as SOFIA, turned its gaze toward our celestial neighbor. Soaring high above the water vapor in Earth's atmosphere, its powerful infrared telescope detected the unmistakable signature of water molecules, H2O, clinging to the soil in a sunlit crater. This was not a trace amount, and it was not locked away in eternal darkness. It was right out in the open. The discovery defied all logic. How could water possibly persist under the sun's intense glare? The leading theory suggests the moon's soil, or regolith, might be like a pumice stone, full of tiny glassy beads created by micrometeorite impacts. These beads could be shielding the water molecules within their microscopic structures, creating tiny, resilient oases scattered across the lunar landscape. This changes everything. Water is the oil of space exploration. It is not just for drinking. It can be split into its core components, hydrogen and oxygen, to create breathable air for astronauts and, most critically, rocket fuel. Finding a ready supply of water on the moon means we might not have to launch every single drop from Earth at an astronomical cost. It opens the door to a permanent lunar base, a refueling station that could serve as a stepping stone, a cosmic gas station on the highway to Mars and the deeper solar system. The silent, dusty plains of the moon may hold the key to unlocking the rest of our celestial neighborhood. The promise of lunar water hints at a future we can almost grasp, but the James Webb Space Telescope is now showing us a past we never imagined. It has peered back over 13 billion years to a time when the first galaxies were just being born and found something that should not exist. Astronomers call them the universe-breaker galaxies. These colossal structures are not the faint, infant smudges predicted by our models. They are massive, fully formed, and staggeringly mature, appearing at a cosmic moment so early that, according to our current understanding, they simply had no time to grow so large. It is like walking into a nursery and finding a room full of adults. The discovery sends a tremor through the very foundations of cosmology. Our standard model of the universe, the Big Bang Theory, provides a detailed timeline for cosmic evolution. It tells us how long it took for the first stars to ignite, how they gathered into small proto-galaxies, and how eons of mergers and accretion slowly built the grand spirals and ellipticals we see today. The universe-breaker galaxies shatter that timeline. They are far too massive, far too soon. The only way they could exist is if galaxy formation in the early universe was not a slow, stately process, but a frantic, explosive burst of creation. This forces astronomers to consider radical possibilities. Perhaps the first stars formed with an efficiency we cannot yet explain. Maybe dark matter, the invisible scaffolding of the cosmos, clumped together much faster than our simulations predict. Some have even suggested this could point to a need for entirely new physics, a revision of the laws that govern cosmic growth. These galaxies are not just ancient relics, they are a direct challenge, a message from the dawn of time telling us that our story of the universe is still missing its most crucial chapters. While the James Webb Telescope unveils a chaotic cosmic dawn, our next great observatory is being designed with a single, profound goal: to stare directly at worlds like our own and search for the chemistry of life. This is the Habitable Worlds Observatory, a mission that represents the next giant leap in our quest to answer humanity's oldest question. Its primary objective is audacious: to directly image at least 25 potentially Earth-like planets orbiting other stars and analyze the light filtering through their atmospheres for the telltale signs of biology. To accomplish this, the telescope will need to be a technological marvel far beyond anything we have launched before. It will likely employ a massive, segmented mirror, even larger than Webb's, and a revolutionary device called a coronagraph. Think of a coronagraph as an ultra-sophisticated sun visor for a telescope. Its job is to block the overwhelming glare of a distant star, millions of times brighter than the small, orbiting planet we want to see. By perfectly cancelling out that brilliant starlight, it reveals the faint, pale blue dot hidden in the glow, allowing us to capture its direct image for the very first time. Once we have that precious sliver of light, the real magic begins. By splitting that light into a spectrum, scientists can read it like a cosmic barcode, identifying which gases are present in that distant world's air. They will be hunting for biosignatures, specific combinations of molecules that, on Earth, are almost exclusively produced by living processes. The most promising combination is oxygen and methane. These two gases are highly reactive and rapidly destroy each other. Finding them together in an atmosphere in significant quantities is a powerful hint that something, perhaps a global network of microbes or a planet-wide forest, is constantly replenishing them. Imagine receiving a spectrum from a planet 50 light-years away and seeing the unmistakable signatures of water vapor, oxygen, and a hint of methane. It would not be proof positive of intelligent life, but it would be the most compelling evidence we have ever obtained that we are not the only living world in the galaxy. The Habitable Worlds Observatory is not just another telescope, it is a time machine for the human spirit, an instrument that could, within our lifetimes, transform a lonely cosmic ocean into a neighborhood teeming with potential. The search for life does not end with the atmospheres of distant planets, but with the chemical whispers hidden within them. Our most powerful tool for this search, the James Webb Space Telescope, recently turned its gaze to a world called K218b, a place that defies simple categorization. Located 120 light-years away, this is not a rocky world like our own, but something far more alien, a Hycean world. Imagine a planet significantly larger than Earth, but with no continents, no mountains, no dry land at all. Instead, it is a global, deep-water ocean wrapped in a thick, hydrogen-rich atmosphere. It is a world of perpetual twilight and crushing pressure, a place where the very concept of shorelines does not exist. The initial data from Webb was already thrilling, confirming the presence of carbon dioxide and methane, which are intriguing but not definitive signs of life. Then came the truly tantalizing clue, a potential signal of a molecule called dimethyl sulfide, or DMS. On our planet, dimethyl sulfide has only one known source, biological activity. It is produced in enormous quantities by marine phytoplankton, tiny algae that form the base of the ocean's food web. Finding this molecule in the atmosphere of a water world is like hearing a familiar chord in a symphony of alien noise. It is a hint, a suggestion that in that vast, dark ocean, a process akin to photosynthesis might be underway, yet scientists are urging extreme caution. The detection is tentative, a faint bump in the data that needs to be confirmed with further, more precise observations. The signal could be a phantom, a trick of the complex atmospheric chemistry, or a subtle artifact in the telescope's instruments. The next step is to point Webb at K218b again and again, gathering more light, refining the spectral barcode, and watching to see if that signature of DMS grows stronger and more undeniable. If it does, the implications are staggering. It would mean that we have not just found a world with the right conditions for life, but one that may already be living. A single, unconfirmed signal from a distant ocean could be the first real evidence that biology is not a unique miracle of Earth, but a common feature of a universe brimming with possibility. The faint, hopeful signals from distant worlds are one thing, but the universe itself has just begun to sing to us in a completely different register. For the first time, scientists have confirmed the existence of a cosmic hum, a low-frequency rumble of gravitational waves that permeates the very fabric of space and time. This is not a sound you could hear with your ears, but a rhythmic stretching and squeezing of space-time itself, a vibration so vast it takes years to measure a single cycle. The discovery was made not by a single telescope, but by a network of them, using the cosmos's most perfect natural clocks, pulsars. These are the rapidly spinning cores of dead stars, beaming out radio waves with the metronomic precision of atomic clocks scattered across the galaxy. For over a decade, observatories like NanoGrav in North America and others around the world have been patiently listening to an array of these pulsars, measuring the exact timing of their pulses with exquisite accuracy. They were searching for a specific pattern, a correlated delay or advance in the ticks from pulsars across the sky. This pattern would be the telltale fingerprint of a gravitational wave, a ripple in space-time, passing through our corner of the galaxy and ever so slightly changing the distance between us and these distant lighthouses. And they found it. The data revealed a background hum, a chorus of waves that is statistically far stronger than anything random chance could produce. So, what is creating this constant, universe-spanning vibration? The leading explanation is as monumental as the hum itself. Astronomers believe this is the collective voice of countless pairs of supermassive black holes orbiting each other in the hearts of distant galaxies. These are not the stellar mass black holes we have detected before, but behemoths, each weighing millions or even billions of times the mass of our Sun. As these cosmic giants spiral inward over millions of years, their immense gravity churns the spacetime around them, sending out these powerful waves. It is the sound of the universe's most violent and invisible dances, a slow-motion waltz that has been ongoing for eons. This discovery opens an entirely new window on the cosmos. We are no longer just seeing the universe, we are now listening to its gravitational symphony, a soundtrack that allows us to study the most massive objects in existence, objects that emit no light at all. This cosmic hum of colliding giants is a soundtrack from the largest scales imaginable, yet some of our most profound discoveries are now arriving in the palm of a scientist's hand. We have reached out and touched the ancient builders of our solar system. Two ambitious missions, NASA OSIRIS-REx and Japan's Hayabusa 2, performed a feat of interplanetary precision, traveling billions of miles to rendezvous with asteroids, collect material from their surfaces, and bring those precious samples home. These were not just rocks, they were time capsules, pristine remnants from the dawn of our planetary system, untouched by the ravages of Earth's atmosphere or geology. The targets were two carbon-rich asteroids, Bennu and Ryugu, thought to be cosmic warehouses of the original ingredients that went into making our world. When the canisters were opened in sterile laboratories, the initial analyses were breathtaking. Scientists found a rich, complex soup of organic compounds, the very kind of carbon-based molecules that are the essential foundation for life as we know it. But perhaps even more significant was the discovery of water, not as liquid but locked inside water-bearing clay minerals. This combination is a revelation. It provides the first direct physical evidence for a theory that has been circulating for decades, the idea that the building blocks for life, the water for our oceans and the organics for our biochemistry, were delivered to a barren, early Earth by a rain of ancient asteroids. Think of our infant planet, a scorching ball of magma, too hot to hold onto any volatile compounds. Then, imagine a relentless bombardment from countless asteroids just like Bennu and Ryugu, each one a delivery truck packed with life-giving materials. They seeded our world with the water that would become our oceans and the complex organic Lego blocks that would eventually assemble into the first living cells. We are, in a very real sense, children of these asteroids. Their ancient cargo, now sitting in labs on Earth, is the closest we have ever come to holding the raw recipe for life itself. The same gravitational waves that let us hear the universe's hum are now revealing a profound discord in our cosmic measurements. Astronomers have two primary ways to measure how fast the universe is expanding, a number known as the Hubble constant. One method uses the cosmic microwave background, the faint afterglow of the Big Bang, as a precise starting point. By extrapolating from that ancient light with our standard model of cosmology, we get one very specific expansion rate. The other method builds a cosmic distance ladder, using pulsating stars and stellar explosions in nearby galaxies to measure distances and velocities directly. Both techniques are incredibly sophisticated, and both should arrive at the same number, yet they do not. The results are stubbornly, consistently different. This is not a small statistical fluke. It is a growing crisis known as the Hubble tension. The universe, according to our best observations, appears to be expanding at two different speeds. It is as if you used two different maps to navigate the same city, and each one gave you a completely different scale for the distance between your home and the grocery store. One of these cosmic maps must be wrong, or perhaps our understanding of the terrain itself is flawed. This is where the mystery deepens into the realm of the truly unknown. The leading suspect for this discrepancy is dark energy, the mysterious force responsible for the accelerating expansion of the cosmos. Our current model treats dark energy as a constant, an unchanging pressure inherent to the vacuum of space itself. But what if that is not true? What if dark energy is not constant but dynamic? It could be evolving, growing stronger or weaker over time. It might even be a new force field we have not yet identified. The Hubble tension could be the first observable clue that our simple description of dark energy, which makes up about 70% of the universe, is fundamentally incomplete. We are being forced to confront the possibility that the dominant component of our cosmos is something far stranger and more complex than we ever imagined. This is not just a tweak to a formula, it is a potential crack in the foundation of modern physics, a whisper from the dark that we are only just beginning to hear. This cosmic discord over the universe's expansion rate is humbling, but an even more profound reordering of our cosmic census is underway, and it involves worlds that drift in absolute darkness. For every star you see in the night sky, there could be a hidden planet floating completely alone, untethered to any solar system. These are rogue planets, and they may be the most common worlds in our entire galaxy. The evidence comes from a subtle but powerful technique called gravitational microlensing. When one of these dark, solitary planets drifts precisely in front of a distant background star, its gravity acts like a tiny lens, bending and magnifying the star's light for a few hours or days. This creates a temporary brightening, a distinctive spike in the data that betrays the planet's invisible presence. Large-scale surveys scanning millions of stars have recorded thousands of these microlensing events, and the statistics are staggering. They suggest there could be trillions of these nomads adrift in the Milky Way, potentially outnumbering the stars themselves. This discovery shatters the classic image of planets neatly orbiting a parent sun. It forces a radical rethink of how planetary systems are born and evolve. Many of these worlds were likely flung from their young, chaotic solar systems by gravitational interactions with giant planets, a sort of cosmic billiards that sent them careening into the interstellar void. Others might have formed directly from collapsing clouds of gas and dust, much like stars, but without enough mass to ignite. This raises a question that pushes the very boundaries of astrobiology. Could life exist on a world with no sun? Imagine a planet with a thick, hydrogen-rich atmosphere acting as an insulating blanket, trapping the feeble heat from the radioactive decay in its core. Deep beneath a possible global ice shell, vast, warm, subsurface oceans could persist for billions of years, completely isolated from the stellar winds and radiation that buffet orbiting planets. Around volcanic vents on the seafloor, a whole ecosystem could be thriving, powered not by sunlight, but by chemical energy and geothermal heat, much like the strange communities we find in Earth's deepest ocean trenches. A rogue planet would be a world of eternal night, its sky an unbroken tapestry of stars with no sunrise ever breaking the horizon. Yet in that profound darkness, in the deep, warm abyss, the chemistry of life might still find a way. The profound darkness of rogue planets speaks to the universe's hidden vastness, but here on Earth we are building networks of light to protect our most sensitive secrets. The race to create unhackable communication has moved into orbit, with satellites performing feats of quantum magic. Scientists have successfully demonstrated quantum key distribution from space, a technology that leverages the bizarre rules of the quantum world to secure data in a way that is, in principle, impervious to any eavesdropper. Here is how it works. At its heart, the system uses individual particles of light called photons. These photons are prepared in specific quantum states, a delicate condition that is instantly disturbed the moment anyone tries to measure them. Imagine sending a message locked in a box, but the box is made of a glass so fine that any attempt to open it shatters the glass and destroys the contents inside. In a quantum communication link, a satellite generates a random sequence of these quantum states and beams them down to two separate ground stations. Those stations then use the properties of the photons they receive to create a secret key, a random digital code that can encrypt a message. Because of the fundamental law of quantum mechanics, if a spy intercepts the photons during their transmission, their very act of observation will alter the photon states. This disturbance creates errors in the key that the legitimate users can easily detect, immediately alerting them that the line is no longer secure. They simply discard that key and generate a new one. This makes the communication channel provably secure, its safety guaranteed not by complex mathematics, but by the unbreakable laws of physics. Deploying this technology from space is the crucial step to making it global. On the ground, these fragile quantum signals can only travel about 100 miles through fiber optic cables before being absorbed. From orbit, a single satellite can blanket entire continents, linking cities thousands of miles apart. This is the foundational architecture for a future quantum internet, a network where not just communication but also computing and sensing are supercharged by quantum phenomena. We are witnessing the birth of a new kind of global infrastructure, one where the strange rules that govern the smallest particles in the universe are harnessed to build a safer digital world for everyone. Mars is a world that keeps its secrets closely guarded, and perhaps none are more tantalizing than the fleeting whispers of methane gas. Our robotic geologist, the Curiosity rover, has been sniffing the thin Martian air for years, and it has recorded sudden, mysterious spikes of this gas. These are not consistent background levels, but dramatic pulses that appear and vanish inexplicably. On Earth, the vast majority of methane is produced by living organisms, from microbes to livestock. It is a clear biological signature. The immediate, thrilling question is whether we are seeing evidence of Martian microbes, perhaps hidden deep beneath the frozen soil, eking out an existence and releasing this gas. Yet the universe rarely offers simple answers. Methane can also be created without any biology at all, through geochemical reactions between water, carbon dioxide, and certain types of rock like olivine in a process called serpentinization. So the detective work becomes incredibly complex. Why does the methane appear in localized plumes and then disappear so quickly? The Martian atmosphere should have compounds that destroy methane over a period of centuries, yet these spikes suggest something is actively producing and releasing it now, and that something is destroying it far faster than we can explain. The European Trace Gas Orbiter, designed specifically to solve this puzzle, has often failed to detect the same methane Curiosity is measuring from the surface. This contradiction deepens the enigma, pointing to a process that is not only sporadic but also incredibly confined, perhaps venting from the ground and dissipating almost immediately. We are left with two equally profound possibilities. We could be witnessing the faint chemical breath of a subterranean Martian ecosystem, a biosphere hidden in aquifers deep below the radiation-scorched surface. Or we are observing the intricate geology of a planet that is far more dynamically alive than we ever believed, with water-rock interactions creating ephemeral pockets of gas. Each erratic pulse on the rover's sensors is a riddle, a single piece of a puzzle that could redefine a world we thought we knew. The faint, erratic pulse of Martian methane is a whisper from a world next door, but we have now captured the portrait of a true cosmic monster. In 2019, the Event Horizon Telescope collaboration unveiled an image that stunned the world, the first direct visual evidence of a supermassive black hole. This was not a simple photograph, but a monumental feat of global coordination. The EHT is not one telescope, but a network of radio observatories spanning the globe, from the high deserts of Chile to the volcanic peaks of Hawaii. By synchronizing them with atomic clocks, scientists created a virtual telescope the size of our entire planet, an instrument with a resolution so sharp it could read a newspaper in New York from a sidewalk cafe in Paris. Their target was Messier 87, a giant elliptical galaxy 55 million light-years away, home to a black hole with the mass of 6.5 billion suns. The image they produced showed exactly what Einstein's theory of relativity predicted: a brilliant, asymmetric ring of light, a whirlpool of superheated gas and dust swirling at nearly the speed of light, encircling a perfect circle of darkness, the black hole's shadow. This shadow is not the black hole itself, for no light can escape its event horizon. It is the silhouette of that point of no return, set against the fiery backdrop of its own accretion disk, a confirmation of gravity warping spacetime so severely that it creates a visible void. The success of this first image was only the beginning. The same global telescope turned its attention to a target much closer to home, the supermassive black hole at the very heart of our own Milky Way, known as Sagittarius, a star. While this black hole is much closer, it was in some ways a harder target to image. It is far less massive than the one in Messier 87, meaning the material orbiting it completes a full rotation in just minutes, causing the light around it to flicker and change rapidly, like trying to get a clear picture of a child running in circles around a campfire. Yet the EHT persevered, and in 2022 it revealed our local cosmic beast. The image was strikingly similar to the first, a glowing ring of light with a dark central shadow, proving the same fundamental physics governs black holes, from the relatively small to the unimaginably large. These images are far more than just pretty pictures. They are rigorous tests of general relativity in the most extreme gravitational environments in the universe. So far, Einstein's century-old equations have passed every test. The size and shape of the shadows match the predictions with astonishing accuracy, showing that even in the chaotic maelstrom at the edge of a black hole, the laws of physics as we know them still hold sway. This does not mean the work is over. Each new observation provides more data, more clues. With future telescopes planned for space and on the moon, we will peer even closer to the event horizon, searching for tiny deviations that might, one day, reveal the subtle fingerprints of new physics, a deeper layer of reality hidden just beyond the shadow's edge. While we map the shadowy edges of black holes, a world we thought we understood has been hiding a fiery secret. Venus, long considered a geologically dead world, has just been caught in the act. A meticulous new analysis of decades-old radar images from NASA, a Magellan spacecraft, has revealed direct evidence of a volcanic vent changing shape and significantly enlarging over a span of just 8 months. This is not an ancient geological feature. It is the unmistakable signature of a recent eruption, proving that the furnace of Venus is still burning. For scientists, this is a paradigm-shifting discovery. We knew Venus was covered in vast volcanic plains and thousands of volcanoes, but without evidence of recent activity, it was easy to assume the planet had cooled and solidified, its internal engine having shut down long ago. This single altered vent changes that entire narrative. It confirms that Venus is a living, breathing world, geologically active right now. Its interior is still churning, still pushing molten rock to the surface, which means the planet is constantly resurfacing itself. This has profound implications for the strange environment high above. The ongoing eruptions pump vast quantities of volcanic gases into that thick, toxic atmosphere. These gases, including sulfur dioxide, are the very chemicals that could potentially provide an energy source for microbial life. In the temperate cloud decks where the phosphine gas was detected, these volcanic outgassings could be fertilizing the atmosphere, offering a chemical buffet for any hardy, floating organisms. The discovery of an active Venus completely reframes the planet from a static corpse to a dynamic world, one where geology and the potential for biology might be deeply intertwined. The planet next door is not just a cautionary tale of a runaway greenhouse. It is a world with a still beating heart, and its volcanic pulse might just be the key that unlocks its greatest mystery. Our own planet's vibrant biosphere might be a cosmic miracle, a fragile bubble of life in an otherwise silent galaxy. This profound silence is the heart of the Fermi paradox, a simple question with terrifying implications. If the universe is so vast and old, teeming with billions of potentially habitable worlds, then where is everybody? One compelling answer is the Great Filter hypothesis, a hypothetical barrier, a cosmic bottleneck that prevents life from advancing to the stage of interstellar colonization. This filter could lie in our past, a challenge we have already unknowingly survived, making us the first and only intelligent life in our galactic neighborhood. Or, chillingly, it could still lie ahead of us in our future, a universal wall that every rising civilization eventually hits and fails to overcome. Recent discoveries are giving us grim new candidates for what this filter might be. We now know that planetary systems are not the stable clockwork we once imagined. The early history of our own solar system was a violent pinball game, with giant planets migrating and flinging asteroids in a cataclysmic bombardment that would have sterilized young worlds. Perhaps this chaotic instability is the norm, and Earth was simply lucky to avoid having its life snuffed out before it even began. Another potential filter could be gamma-ray bursts, the universe's most powerful explosions. These beams of concentrated death, erupting from dying stars or colliding neutron stars, could periodically scald entire galaxies, wiping clean any complex life that had managed to evolve. A burst within a few thousand light-years would be enough to strip our planet's ozone layer for a decade, bathing the surface in lethal ultraviolet radiation and triggering a mass extinction. The eerie silence we observe could be the aftermath of such a galactic sterilization event. Or perhaps the filter is even more subtle, woven into the very fabric of evolution itself. The leap from single-celled microbes to complex, multicellular life took over 2 billion years on Earth. What if that transition, the cooperation of cells to form a unified organism, is the real miracle, an event of such staggering improbability that it almost never happens elsewhere? The Great Filter forces us to look in the mirror. Our own technological adolescence, with its risks of nuclear war, engineered pandemics, or runaway artificial intelligence, could be the very type of challenge that no civilization manages to pass. The silence of the cosmos might be the answer to our paradox, a warning that the final test is one we have yet to face. Our own planet's silent skies might be the exception, not the rule. Far beyond the orbit of Mars, a small, icy moon of Jupiter is actively reaching out into the void. Europa, a world encased in a global crust of ice, has long been a prime target in the search for life. But the challenge seemed insurmountable. How could we ever hope to study an ocean buried beneath ice that could be miles thick? The answer came not from a lander, but from a telescope. The Hubble Space Telescope and later the James Webb Space Telescope have observed something extraordinary: sporadic, towering plumes of water vapor erupting from fractures in Europa's icy shell. jetting hundreds of miles into space. These are not constant geysers, but fleeting, powerful events, like a breath held for centuries and then finally exhaled. They are a cosmic invitation. These plumes are a direct sample of the vast, global ocean hidden below. As the water erupts, it carries with it particles and molecules from the deep, potentially even biological material, spraying it out into the vacuum where our orbiting observatories can analyze it. This changes the entire mission profile for finding life. We no longer need to design a complex nuclear-powered drill to melt through the ice. Instead, a future spacecraft could simply fly through one of these plumes, much like a whale filtering plankton from the sea, and taste the contents of Europa's ocean directly. What might it find? The ocean below is thought to be twice the volume of all Earth's oceans combined. A dark, salty sea in constant contact with a rocky seafloor. There, around hydrothermal vents, the same kind of chemical energy that fuels entire ecosystems at the bottom of our own oceans could be providing the sustenance for life. Flying a probe through a plume is our best and perhaps easiest chance to answer one of humanity's biggest questions. Is there a second genesis of life right here in our own solar system, swimming in the abyss of a frozen moon? The beautiful simplicity of Einstein's universe is beginning to fray at the edges. We are now confronting a crisis in cosmology that runs far deeper than just two conflicting expansion rates. Another profound anomaly has emerged, one that challenges our understanding of the universe's very structure. When we look at the distribution of galaxies across the cosmos, we expect to see a certain level of smoothness, a relic of the universe's rapid inflationary beginning. The Standard Model predicts how this primordial smoothness should have evolved into the cosmic web we see today. But our most detailed maps, like those from the Dark Energy Survey, reveal a universe that is subtly, yet unmistakably, too lumpy. The clumps of matter, the vast galaxy clusters, and the empty voids between them are more pronounced than our theories say they should be. This unexpected lumpiness, combined with the stubborn Hubble tension, creates a 1-2 punch against our established cosmic story. It is as if we have two different blueprints for the same house, and both of them are wrong in fundamental ways. The foundation of modern cosmology, the lambda cold dark matter model, is now shaking under the weight of these inconsistencies. This model relies on two great unknowns: dark matter to provide the gravitational glue for structures, and dark energy to drive the accelerating expansion. For decades, this recipe worked beautifully to explain our observations. Now it is failing to match the data. The cracks are forcing physicists to consider radical revisions. Perhaps dark matter is not cold and sluggish, but warm, made of faster-moving particles that would naturally suppress the formation of small-scale lumps. Or maybe dark matter is not a single substance at all, but a mixture of different, exotic particles interacting in ways we have not yet imagined. An even more profound possibility is that we have been wrong about gravity itself. Theories like modified Newtonian dynamics, or MUND, propose that Einstein's theory of general relativity, while spectacularly successful in our solar system, may need adjustment on the vast galactic scale. This would mean the force that holds the universe together is not quite what we think it is. We are at a crossroads, staring at a collection of clues that point toward a reality far stranger than our standard model allows. The universe is not just expanding, it is sending us a clear message that we are missing something fundamental, a hidden ingredient or a misunderstood law that governs everything. Even as our cosmic models strain under new data, a powerful new ally is emerging to help us make sense of it all. The torrent of information pouring from our observatories is so vast that no team of human scientists could ever hope to sift through it all. This is where artificial intelligence enters the stage, not as a replacement for human curiosity, but as an essential partner in discovery. Machine learning algorithms are now being trained to perform the meticulous work of finding exoplanets with a speed and accuracy that dwarfs human capability. They analyze the faint, rhythmic dimming of a star, the telltale sign of an orbiting planet, and can identify candidates from years of data in a matter of days. This has led to the confirmation of thousands of new worlds, building a rich catalogue of alien solar systems that would have taken us decades to compile. But our eye's role goes far beyond planet hunting. It is learning to classify galaxies by their shapes, sorting spirals from ellipticals with a glance, and identifying rare, distorted galaxies that have been wrenched out of shape by cosmic collisions. Most excitingly, these systems are now being designed to find the anomalies, the objects that do not fit any known pattern. And our eye scanning a star field might flag a source that flickers in a strange, unpredictable rhythm, or a patch of infrared light that is just a little too red, a little too odd. It is in these statistical outliers, these cosmic misfits, that the next great revolution might be hiding. What if the first sign of an alien megastructure or a completely new type of stellar object is not found by an astronomer at an eyepiece, but by a silent algorithm working tirelessly through the night? This is the new paradigm. We are no longer just building bigger telescopes, we are building smarter ones, creating a symbiotic relationship between human intuition and machine precision to explore a universe whose complexity we are only just beginning to grasp. While our algorithms scan the stars, one spacecraft has performed a feat of pure daring, flying into the inferno of our own star. The Parker Solar Probe did what was once thought impossible. It physically entered the Sun's atmosphere, diving deep into the superheated corona. This was not a distant observation, but a direct plunge into a region where temperatures soar to millions of degrees. To survive, the probe relied on a revolutionary heat shield, a carbon composite guard that kept its instruments at room temperature while withstanding a relentless bombardment of radiation and plasma. Its mission was to solve a fundamental solar mystery, the origin of the solar wind. This is the constant stream of charged particles that flows from the Sun and bathes the entire solar system, shaping the magnetic environment of every planet. For decades, we knew this wind existed, but we did not understand its engine. Parker discovered the answer in the corona itself. The data revealed that the solar wind is not a smooth, uniform flow, but is powered by massive, sudden jets of material. The probe found evidence of what scientists call switchbacks, dramatic S-shaped kinks in the Sun's magnetic field lines. Imagine a whip being cracked, but on a solar scale. These magnetic whips snap with incredible force, flinging plasma out into space at tremendous speeds. This is the primary mechanism that accelerates the solar wind, turning it from a gentle breeze near the Sun into the powerful stream that travels across billions of miles. Understanding this process is not just an academic exercise, it is vital for our technological civilization. The most energetic eruptions from the Sun, coronal mass ejections, ride on this solar wind. When these billion-ton clouds of magnetized plasma slam into Earth's magnetic field, they can create severe geomagnetic storms. These storms have the power to induce massive electrical currents in our power grids, causing widespread blackouts. They can disrupt satellite communications, knock out GPS systems, and pose a serious radiation risk to astronauts in orbit. By tracing the solar wind back to its source, the Parker Solar Probe gives us a critical head start. We can now better model the Sun's behavior and predict when these potentially catastrophic space weather events are coming, allowing us to shut down vulnerable systems and protect the infrastructure that modern life depends on. This intimate touch of the Sun has revealed the inner workings of our star's stormy heart, turning its greatest dangers into a phenomenon we can finally begin to foresee. The hunt for life's simple chemistry now expands into a search for the glow of cosmic cities. This is the frontier of technosignatures, evidence not of biology but of technology, a deliberate broadening of our quest for intelligence. We are no longer just looking for the chemical fingerprints of microbes or algae. We are scanning the heavens for the artifacts of a civilization advanced enough to reshape its world or its star. Imagine peering at a distant exoplanet as it passes behind its sun, and in the faint darkness of its night side, detecting a concentrated patch of light entirely different from the soft glow of reflected starlight. This could be the artificial illumination of a vast metropolitan area, a signature of a world that has conquered its own night. Or consider a star whose light periodically dims in bizarre, unnatural ways, not the clean curve of an orbiting planet, but a jagged, geometric pattern. This could hint at a megastructure, a vast swarm of energy collecting satellites encircling the star, a Dyson sphere under construction harvesting a sun's entire output. Even a planet's atmosphere could betray a technological hand. We might detect synthetic gases with no natural explanation, like chlorofluorocarbons from an industrial civilization, lingering in the air as an unintended beacon of their presence. This shift from biosignatures to technosignatures is profound. It acknowledges that a truly intelligent species might leave a mark on its environment that is far clearer and far more detectable across interstellar distances than the subtle imbalance of oxygen and methane. We are training our most powerful telescopes to look for the shine of engineering, the silhouette of ambition, and the chemical traces of industry. It is a search for a reflection of our own possible future, a silent question cast into the dark: are we the only ones building? Our search for cosmic cities is matched by our ability to sense the universe's most elusive messengers. Deep in the ice of the South Pole, a cubic kilometer of pristine frozen water serves as the heart of an experiment called IceCube. Its target is the ghost particle, the neutrino, a subatomic wisp so indifferent to matter that trillions pass through your body every second without a single interaction. In September 2017, IceCube detected a single neutrino with unprecedented energy, a particle that had screamed across the cosmos. It issued an instant alert to astronomers worldwide. Telescopes of every kind swiveled to the coordinates, and they found the source, a blazing object 4 billion light-years away known as a blazar. A blazar is the core of a distant galaxy, centered on a ravenous supermassive black hole. Unlike the quiet beast at our galaxy's center, this one is actively feeding, and it has aimed one of its powerful jets of radiation and particles directly at Earth. That single high-energy neutrino was a bullet fired from this cosmic cannon. This event was a landmark because it was not observed with light alone. For the first time, we had combined a neutrino detection with traditional electromagnetic observations, from radio waves to gamma rays. This is the power of multi-messenger astronomy. Think of a cosmic explosion as an orchestra. Before, we were only able to see the performance, the light show. Now we are learning to hear the music, to feel the vibrations. With multi-messenger astronomy, we combine different senses. We see the light, we feel the gravitational waves rippling through space-time, and we catch the ghostly particles that carry information from the very heart of the cataclysm. Each messenger tells a different part of the story. Light shows us the heat and the shock waves. Gravitational waves reveal the choreography of massive objects merging. And neutrinos, born in the furious particle accelerators near the black hole's event horizon, give us a direct look at the engine itself. This single ghost particle, traced across the universe, did more than just point to a blazar. It heralded a new era of holistic observation, where we no longer just watch the universe's most violent events, we experience them with every sense we possess. The familiar shoulder of the constellation Orion seemed to falter. Betelgeuse, one of the brightest stars in our sky, began a dramatic and unexpected fade. For months, starting in late 2019, its light dwindled to a dimness never recorded in modern history. The astronomical world held its breath. Was this the final act, the prelude to a supernova explosion that would outshine the full moon? Telescopes of every kind were immediately trained on the red supergiant, and the answer they pieced together was not a death rattle but a cosmic sneeze. The star had not collapsed, it had coughed. Detailed analysis revealed that Betelgeuse had ejected a colossal cloud of its own material, a massive stellar burp. This hot gas traveled away from the star, cooling as it expanded until it condensed into an enormous cloud of dark, obscuring dust. For a time, this veil of stardust drifted between Betelgeuse and us, blocking a significant portion of its light and causing the great dimming. This event was a rare, real-time glimpse into the violent and messy final chapters of a giant star's life. Betelgeuse is a ticking bomb, a star so massive it is destined to end its life in a supernova. In its old age, it has become unstable, pulsating and heaving as it fuses heavier and heavier elements in its core. These giant convulsions eject vast quantities of material into space, building up the cosmic dust and gas that will one day form new stars and planets. The Great Dimming was not the end of the story, but a vital piece of it. It showed us that the final millennia of a supergiant's life are a turbulent, active process of self-destruction. The star is literally shedding its own skin, preparing for the ultimate detonation. We now understand that this kind of dramatic dimming is a natural part of the life cycle for stars of this type. It means the next time Betelgeuse fades, we will watch with a different kind of anticipation, knowing we are witnessing the final, restless breaths of a cosmic giant. The final, restless breaths of a giant star seed the cosmos with the dust for new worlds, and for the first time, we can now witness that incredible act of creation in breathtaking detail. Far from the chaotic end of Betelgeuse around younger, calmer stars, the very process of planet formation is being captured in images so sharp they feel like a glimpse into a cosmic nursery. The Atacama Large Millimeter Array, or ALMA, a network of radio telescopes high in the Chilean desert, has given us our first clear view of protoplanetary disks. These are vast, pancake-shaped rings of gas and dust that swirl around infant stars, the raw material from which solar systems are built. Earlier telescopes saw only hazy blobs, but ALMA vision revealed intricate structures within these disks, features that tell a dynamic story. We see dark, clean gaps carved within the bright dust, like lanes being cleared in a crowded highway. These gaps are the gravitational sweep of infant planets, already large enough to pull in material and push aside the debris in their path, sculpting their own orbits. We see elegant spiral arms, swirling patterns that ripple through the disk like cream stirred into coffee. These spirals are often the gravitational wake of unseen planets, their presence warping the entire disk around them. And we see bright clumps and asymmetries, concentrations of material that could be the very seeds of future gas giants, the points where dust is beginning to coalesce under its own gravity. These are not artists' impressions, they are direct observations, the fingerprints of planets caught in the act of being born. The James Webb Space Telescope has added its own infrared eyes to this investigation, peering through the obscuring dust to see the warmer material closer to the star. Together, these observatories are creating a moving picture of planetary birth, showing us that our own solar system's formation was not a serene, orderly process, but a vibrant, chaotic, and beautiful construction project, one that is happening right now around countless stars across the galaxy. Far beyond the familiar orbits of Neptune and Pluto, the outer solar system holds a gravitational secret. For years, astronomers have tracked a peculiar clustering in the paths of small, icy bodies in the distant Kuiper belt. These objects, known as trans-Neptunian objects, do not follow the randomly oriented orbits we would expect. Instead, their elongated paths are mysteriously aligned, as if an unseen hand is herding them. The most compelling explanation for this gravitational choreography is a hidden planet, a world several times more massive than Earth, lurking in the perpetual twilight of our solar system's frontier. This hypothetical world is known as Planet 9. The evidence is purely gravitational, a ghostly signature written in the wobbles of distant ice dwarfs. Based on the way these small bodies are grouped, scientists have calculated a probable orbit for Planet 9. It would be a colossal loop, taking 10,000 to 20,000 years to complete a single journey around the Sun. At its closest approach, it might come within a few hundred astronomical units, but at its farthest, it would be a staggering 1,000 times farther from the Sun than Earth. This would be a world of unimaginable cold and darkness, a gas-shrouded ice giant or a super-Earth, so distant that the Sun would appear as nothing more than a particularly bright star in its black sky. The hunt for this phantom planet is one of astronomy's great modern quests. Powerful telescopes like Subaru in Hawaii are methodically scanning the vast predicted orbital path, looking for a single, faint point of light moving slowly against the background of fixed stars. It is a painstaking search, like finding one specific grain of sand on a beach the size of a continent. Discovering Planet 9 would be far more than just adding a new world to our solar system's map. It would be a monumental validation of gravitational prediction, a modern-day echo of the discovery of Neptune. Its existence would force us to completely rewrite the story of our solar system's formation and dynamic history. How did such a large world end up so far away? Did it form closer in and get flung outward by a gravitational interaction with Jupiter or Saturn? Or is it a rogue planet captured by our Sun's gravity in the system's chaotic youth? Finding this hidden giant would not only solve one mystery, it would open a new chapter in our understanding of the cosmic forces that built our celestial home. While our telescopes map the cosmos on its grandest scales, a far quieter revolution is taking place in the microgravity laboratories orbiting high above our heads. The International Space Station has become a testing ground for some of the most delicate experiments ever conceived, ones designed to answer a question that has stumped physicists for a century. Is gravity a quantum force? Our two most successful theories of reality, general relativity and quantum mechanics, describe the universe in brilliantly accurate but fundamentally incompatible ways. General relativity paints a smooth, geometric picture of space-time, where gravity is the curvature created by mass and energy. Quantum mechanics reveals a fuzzy, probabilistic world where particles can be in two places at once. The chasm between them is the greatest unsolved problem in fundamental physics. To bridge it, we must discover if the fabric of space-time itself is quantized, broken into tiny, indivisible pieces. This is where the unique environment of space becomes essential. On Earth, gravity relentlessly pulls every object toward the ground, making it nearly impossible to isolate and observe the subtle quantum behaviors of relatively large objects. But in the continuous freefall of orbit, true microgravity is achieved. Here, scientists can perform experiments that are simply not possible in any lab on the ground. One such experiment involves cooling clouds of atoms to temperatures 1 billion times colder than deep space, creating a state of matter known as a Bose-Einstein condensate. In this bizarre condition, millions of atoms begin to behave as a single quantum wave. On the space station, these fragile quantum waves can be observed for much longer periods than on Earth, free from the distorting effects of gravity. By studying how this wave of matter behaves, physicists can search for minuscule deviations that might reveal the quantum nature of gravity itself. Other missions involve precisely dropping test masses inside shielded capsules, watching their motion with lasers to see if gravity causes any quantum decoherence, a telltale blurring that would occur if gravity is not a continuous field but is carried by discrete particles known as gravitons. Finding evidence for gravitons would be a discovery on par with the confirmation of the Higgs boson, fundamentally rewriting our understanding of how the universe is constructed at its most basic level. The answers we seek are not written in the light of distant stars, but in the impossibly quiet fall of an atom in the vacuum of space, a search for the faintest of whispers that could finally unite our two pictures of reality. The silent, dark expanse between stars holds a secret about the end of things. The James Webb Space Telescope has now looked back in time and found entire cities of suns that were already dead when the universe was in its infancy. These are massive galaxies, fully formed and rich with ancient stars, but they had mysteriously run out of fuel. Their reservoirs of cold hydrogen gas, the raw material for building new stars, were almost entirely depleted. Astronomers call them quenched galaxies, and their existence so early in cosmic history is a profound puzzle. A galaxy is a star-making factory, and for it to simply stop working, something must have happened to halt the production line with brutal efficiency. The leading suspect is the galaxy's own supermassive black hole. As these monstrous engines feed, they can become active galactic nuclei, blazing with intense radiation. The energy pouring out can heat the surrounding gas, preventing it from cooling and collapsing into new stars. In more violent scenarios, the black hole can drive powerful jets that physically blow the star-forming gas right out of the galaxy, leaving it barren. This is a form of cosmic feedback, a self-regulating mechanism where a galaxy's central beast effectively starves its own future. But the timing is what defies all expectation. For these early galaxies to have formed so many stars so quickly, and then for their black holes to have grown massive enough to trigger this quenching, all within the first few billion years after the Big Bang, suggests a frenzy of activity that our current models of galaxy evolution simply cannot account for. It paints a picture of a much more explosive and abrupt youth for the universe, where galaxies lived fast and died young, their lights going out long before their time. What catastrophic event could silence a cosmic metropolis so completely and so soon? The ocean floor off the coast of Papua New Guinea holds a secret, one that may have arrived from another star. In 2014, a fireball streaked through the sky and splashed into the sea, an event logged by government sensors as CNEO's 2014-0108. For years, it was just another meteor. Then, Harvard astrophysicist Avi Loeb and his team analyzed its trajectory. Their calculations suggested this object was moving at speeds that could only mean one thing: it was not from our solar system. It was an interstellar meteor predating Oumuamua by 3 years, but the story did not end there. The data also indicated this object was exceptionally tough, surviving its atmospheric entry with a material strength far greater than that of most stony meteorites. This unusual durability led to a bold and controversial hypothesis. Perhaps this was not a natural rock at all, but a piece of alien technology, a probe or a fragment of a spacecraft from a distant civilization. The scientific community reacted with intense skepticism, and rightly so. The standard for such an extraordinary claim is extraordinarily high evidence. The data itself came from a United States government sensor, likely a missile warning satellite, and its full accuracy and uncertainty were classified, making independent verification difficult. Many astronomers argue the object's high speed and strength could be explained by a rare type of iron-rich asteroid, a natural visitor from a faraway system. The core of the scientific process is healthy doubt, a demand for repeatable observations and open data. This is not a rejection of new ideas, but a necessary filter to separate genuine breakthroughs from statistical noise or measurement error. Undeterred by the controversy, Loeb mounted $1 million expedition to the calculated impact zone. His team dragged a magnetic sled across the seabed, searching for tiny fragments. They recovered numerous metallic spherules, little beads of material, and initial analysis suggested a unique chemical composition unlike any known solar system alloy. The investigation is ongoing, a meticulous sifting of evidence from the deep. This is how science grapples with the truly unknown, not with immediate acceptance but with rigorous, painstaking collection. Whether these fragments are the shattered remains of an interstellar asteroid or something far more profound, their retrieval is a testament to human curiosity. We are now literally sifting the ocean floor for pieces of a visitor from the void, determined to hold a piece of another star system in our hands and finally know its truth. Sometimes the most seductive ideas are the ones that promise to break the rules. For years, a concept known as the M-Drive captivated the world with a tantalizing possibility, a rocket engine that needed no fuel. The principle was simple in its audacity. By bouncing microwaves around inside a sealed, cone-shaped metal chamber, the device supposedly created a net thrust, a push in one direction without expelling anything out the other end. It was a reactionless drive offering the dream of limitless exploration, a way to propel spacecraft to the stars without the colossal weight of propellant. The initial laboratory reports were electrifying, showing small but measurable amounts of thrust from tabletop prototypes. The scientific community was immediately skeptical, and for a very good reason. The M-Drive seemed to blatantly violate Newton's third law of motion, the fundamental principle that for every action there is an equal and opposite reaction. A car moves forward because its tires push backward on the road. A rocket accelerates upward because it throws hot gas downward. The M-Drive proposed to do the work of the car without touching the road or the rocket without the exhaust. It promised something for nothing, a perpetual motion machine for the space age. Yet the glimmer of potential was so revolutionary that several teams, including one at NASA EagleWorks laboratory, dedicated serious effort to testing it. They built their own versions, isolating the devices in vacuum chambers and using exquisitely sensitive pendulums to measure any force. For a time, the mystery deepened. Some tests still showed a tiny, anomalous thrust, a whisper of push that defied easy explanation. Hope, however, is not a scientific instrument. The real work of science is not just in discovery, but in the relentless pursuit of error. As more rigorous experiments were conducted, the truth slowly emerged. One by one, the potential sources of that phantom thrust were identified and eliminated. It turned out that thermal expansion, the simple heating of the device during operation, could create a tiny mechanical shift that mimicked thrust. The Earth's magnetic field and subtle interactions with the test apparatus itself were also found to be culprits. In the most definitive tests, when every possible variable was accounted for, the thrust vanished. The M-Drive had not broken the laws of physics. It had simply highlighted the immense difficulty of measuring forces at the very edge of detectability. Its ultimate demise was not a failure but a triumph. It was a powerful demonstration of the scientific method in action, a self-correcting process that is far more valuable than any single fleeting anomaly. The process itself is the engine of real discovery, one that, unlike the mythical drive, actually moves us forward. These lingering questions from the past are precisely what the next generation of telescopes is being built to answer. On remote mountaintops in Chile, engineers are assembling the giants of tomorrow, instruments so powerful they will transform faint smudges of light into sharp, detailed worlds. The Extremely Large Telescope, or ELT, is a staggering project. Its main mirror is not a single piece of glass, but a mosaic of 798 individual hexagonal segments, working together to form a light-collecting surface nearly 40 meters across. That is wider than a blue whale is long. Alongside it, the Giant Magellan Telescope, or GMT, is forging its own path with a mirror composed of 7 of the largest, most perfect glass casts ever made, each one over 8 meters wide. These are not just incremental improvements, they are leaps that will redefine observational astronomy. Their primary weapon is sheer light-gathering power. Imagine trying to read a book in a dim room with a small flashlight. You might make out a few words. Now, switch on a powerful stadium light. Every detail on the page becomes crisp and clear. That is the difference between our current telescopes and these new behemoths. They will collect so much light from distant objects that their resolution will be unprecedented. They will be able to see an astronaut on the moon, if one were there, and distinguish the individual headlights of a car on Mars. This power will be directed at 2 of the universe's greatest mysteries. The first is the direct imaging of Earth like exoplanets. Right now, finding a pale blue dot orbiting another star is like trying to see a firefly hovering next to a massive, blazing searchlight from thousands of miles away. The ELT and GMT, equipped with advanced coronagraphs, will be able to blot out that brilliant stellar searchlight with incredible precision. For the first time, we will not just infer a planet's existence from a wobble or a shadow, we will see it as a distinct point of light. We will be able to take its spectrum and analyze its atmosphere for the definitive signs of oxygen, water vapor, and methane, the chemical triad that screams of a living world. The second great mission is to peer into the deepest past to the very first galaxies. The James Webb Space Telescope showed us that these ancient structures exist, but they are still faint, unresolved blobs in its images. The ELT will transform those blobs into swirling, structured galaxies. We will see their spiral arms, their bright cores, and the clusters of young, hot stars within them. We will watch in a single snapshot how galaxies look just a few 100 million years after the Big Bang, giving us a family album of the universe's infancy. These telescopes will not just show us more, they will show us everything in a new light, turning the final page on cosmic mysteries we have pondered for centuries and beginning a new book whose first chapters we cannot yet even imagine. From the potential whisper of life in the clouds of Venus to the silent hum of colliding black holes, these 30 discoveries are not isolated facts. They are a chorus of revelations, each one a crack in the facade of our ignorance, letting in a little more light. Every unexplained signal, every ancient galaxy that should not exist, every water molecule on a sunlit moon is a testament to a universe that is far stranger, more dynamic, and more wonderful than we ever dared to believe. They prove that the edge of knowledge is not a final frontier, but a shifting horizon, constantly pushed back by our relentless curiosity. We are living in a golden age of cosmic exploration, a time when the fundamental stories we tell about our place in the cosmos are being rewritten before our very eyes. So the next time you find yourself under a clear night sky, look up, let your eyes trace the familiar constellations, and then remember the hidden truths lurking just beyond the light. Remember the rogue planets drifting in eternal night, the quantum whispers in the void, and the phantom worlds waiting for their portrait to be taken. The greatest discoveries are not behind us. They are waiting in the data, in the next observation, in the next question we are brave enough to ask. The next revelation that changes everything could be announced tomorrow. Stay curious.